My name is Smita Chatterjee, and I'll be presenting on the stability of Ig domain unfolding within Titin. Now, what is Titin? Titin is a giant protein contributing to the elasticity of muscle fibers. When we see muscles on a real-world scale, what we see are bundles. Bundles are further broken up into muscle fibers, which are composed of single contractile units called sarcomeres. Sarcomeres extend from Z disc to Z disc, and the stacking of these sarcomeres from end to end is what produces the muscle fiber. When we think of contraction, contraction relies on a three-filament system. We have the thin actin filament in blue, the thick myosin filament in red, and the elastic titin filament in black. Now, when the muscle shortens or lengthens, the filaments lengthen and shorten accordingly by sliding against one another. So how does the sarcomere know what length to return to? After all, there is a physiological normal resting length of our muscles. This is due to the elasticity of titin, which acts as a rubber band, snapping the sarcomere back into place, as we can see here. Now, if we look at the actual extension of titin upon muscle stretch, we can see that at a resting physiological length, we have titin resting in a furled state with the Tandem Ig, N2A, and PEVK regions over here. Now, at a low force, we see an extension of the proximal tandem Ig segment in orange. And then at higher forces, we see the PEVK region in green extending. Now, the actual modality of Titin has been posited to exist as a beads on a string model, with repetitive Ig domain structures along the entire length of the molecule, straightening out as we extend the sarcomere further and further. Now, the extension of the muscle itself has been demonstrated to extend even further than would be possible if these beads were just straightening out. So we hypothesized that the domains themselves, these Ig domains, are actually unfolding. That is to say, the beads themselves are unfurling to produce an even longer length. So how do we test this? We test this to see how easily these domains will unfold, because if the domain can easily unfold, it is more possible that it will happen in the actual muscle. We do this by doing chemical and thermal denaturation, in which we apply an external stress to the protein and see how easily it unfolds. We did this for domains I65 through I70. As we can see here, the delta G unfolding values are representative of the ease of which the protein is likely to unfold. Delta G is typically within 5 to 15 kilocalories per mole for standard proteins, and as we can see here, we have alternating sequences available. Conclusions: it is indeed possible for these domains to unfold under certain stresses, and as always, further studies are needed to confirm these effects and see across several different Ig domains.